thank you everybody for joining us today for the CCTF Technical Exchange on Clock Data Analysis and Visualization. We're going to have a very interesting talk today by both Yuko Hanado, formerly from NICT, and Bharath Vattikonda. So today, our speakers are going to be speaking to us about the importance of clock data analysis, because the quality of the clock data that's submitted to the BIPM is very important in terms of being able to generate UTC. So we're going to start first with a tutorial by Yuko. And then we are going to move on to a live demonstration of some CBKT e-learning resources that were developed by Bharath Vattikonda. I would like to highlight the fact that this is a newly released course on the CBKT website. If you go to elearning.bipm.org, you'll be able to access this course. It's called Clock Data Checking. So I just want to give you a little bit of information on how to get there. So to access the BIPM e-learning site, you can go to elearning.bipm.org and then filter by provider, which is going to be BIPM courses, and then click time and frequency, which is down here on the second set of topic filters. And then you can click on clock data checking. And what you can do is you will be asked to create a login to access the course. And from there, what you'll be able to see once you have access to the course is you'll be able to see a tutorial which provides tips and guidance on how to visualize and do data analysis on your clock data. A very important part of this e-learning resource is that there is online software that everybody can access. Today, we're going to be accessing this clock data analysis tool from this link. I'm going to put it into the chat in case anybody doesn't know how to get to it. An additional set of resources on this e-learning page is also a video demonstration on the usage of how to actually use the application, along with a user manual. Also provided is sample data set. So hopefully all of you received an email that gives you the link for where to find this online resource, and also a sample data set. Excuse me, I think somebody is unmuted. Can everybody mute themselves?
Audio.
Perfect. Thank you. So if for some reason you had some difficulties accessing the sample data, if you go to this course, that's the same sample data is on the same website, so you can download it from there. And in addition to that, there are a set of resources. Before we begin, I'd like to mention that currently the application that's been developed is on a platform that might be a little bit slow for today, but the BIPM is creating a new cloud access for faster performance that will be available in the future. So with that, I'm going to stop sharing. I would like to begin by introducing Yuko. So Yuko Hanado retired from the NICT in 2023 and is currently involved as a cooperative visiting researcher there. She was engaged in work to generate and maintain Japan Standard Time for more than 20 years. Her field of research is in algorithms for averaged atomic timescales. So with that, I'd like to invite Yuko to share her screen.
Thank you, Tara, for introducing me. So my name is Yuko Hanado, and I'm sharing my screen. Can you see my presentation file? Can you hear my voice?
Yes.
Okay.
Yes.
Then let's start from the slideshow. Is it okay?
Right now, I'm seeing the presenter.
Okay.
Slide. Presenter mode.
Is it okay?
That's perfect. Thank you so much.
Okay. So I'd like to start my talk. Okay. Then the title of my talk is Clock Data Checking, and in this talk, I'd introduce some basic techniques that are useful for checking measured clock data. Clean clock data improves the quality of time scale. So let's learn how to process, check, and verify your clock data. This is the contents. In the first part, some misleading examples are introduced to show why the data checking is so important. In the second part, some tips for detecting bad data are introduced. In the last slide, I'd like to mention about some points to keep in mind in the data processing. Then, let's start the first part. Needless to say, the quality of clock data will directly affect the quality of atomic time scale. No matter how good clock you have, however, bad data added at the measurement may mask the actual quality of the clock. Therefore, precise data check is so important. The following 3 slides provide some potentially misleading examples. So, the first one, example 1, is degraded evaluation due to outliers. Example 2 is overlooking outliers due to a large slope. And example 3 is overlooking abnormal trend masked by large noise. So let's start from example 1. It shows a degraded evaluation due to outliers. Plot A shows the true performance of the clock. However, if outliers, usually due to the instrumental trouble, are included, the standard deviation may look worse than true performance of the clock. Example 2 shows the problem of overlooking outliers due to large slope. In plot A, we can easily recognize the outlier. However, if a large trend exists in addition, like in the plot B, outliers are hidden so that we overlook them. The last example shows the problem of overlooking abnormal trend masked by large noise. The former example in the previous page showed the outlier masked by a linear trend. Inversely, there may be a case that systematic trends are hidden in the noise. The plot B actually contains a sine wave as in the plot A. However, it is not obvious by a large white noise. For getting the true performance of the clock from its measurement data, I would introduce here 5 simple methods for checking the clock data. Tip 1 is plotting the whole dataset plus zooming the scale. Tip 2 is removing evident trends. Tip 3 is smoothing, that is moving average. Tip 4 is checking the continuity of data sampling. And tip 5 is checking the distribution of sampled data. The first tip is plotting the whole dataset plus zooming the scale to identify possible bad data. Plotting the whole dataset is effective for grasping a general tendency. In the plot A, we can find an outlier. In addition, there seems to be a quadratic trend, but it is less obvious in this plot. By expanding the scale, like in plot B, the quadratic trend becomes more apparent. In addition, we can find a small outlier and a phase offset that were not visible in the plot A. The tip tool is removing evident trends. Removing an evident trend helps to detect outliers or small other trends. For example, an outlier masked by a large slope in the plot A becomes clear in the plot B by removing the trend. Tip 3 is smoothing, for which a moving average is often used. Moving average helps to detect a long-term trend. Here, please note that fluctuations shorter than the average interval are not visible in the moving average. In the plot A, 4-hour periodic trend is hidden under the white phase noise, but it is not obvious. However, in the plot B, by proceeding a moving average over 1 hour, the result in yellow line suggests this periodical trend in red. Tip 4 is checking the continuity of sampling duration. Overlooking of missing data can cause fails discontinuity of the data. In the plot A, a phase jump seems to occur, but it is a misunderstanding due to absence of correct time stamping. This misunderstanding is caused by missing data being not properly taken into account. In plot B, the gray line with the correct time stamp shows the true normal behavior. The last tip is checking the distribution of sampled data. Abnormal data distribution may indicate some troubles in the process. Here, plot A and plot B show the same standard deviation, but the data distribution are different. In fact, plot B is a result of occasional phase jumps of 20 nanoseconds has been occurred in the C data. If without such 20 nanosecond phase jump in B, the true clock performance would be like C. However, it is difficult to notice that without the distribution plot. In fact, observing the distribution of B precisely, the peak offset around 20 nanoseconds can be seen, and this fact gives us the useful information. That's all for the mentioned tips, and here is the summary and important notes. Data checking is so important to know the true condition of your data. Measurement data often becomes dirty due to many non-essential causes, such as instrumental anomalies, non-stable power supply or room temperature, inappropriate pre-processing, etc. To analyze the data from various standpoints is so important to maintain the essential quality of measurement data. Several tips can be used for detecting bad data or strange behavior. The mentioned tips are primitive, but useful to notice the anomalies easily and quickly. Data checking may help to improve your UTC-K timescale and the data submitted for UTC. And lastly, I'd like to emphasize the following. If anomalies are detected, please investigate their origin and try to remove the originating cause. Bad data tell you so much information of the systems. It's not recommended to only remove bad data. If the anomalies are due to system trouble, other future measurement data may include other anomalies. In such a case, removing the spotted bad data may not be enough. Please check the origin of anomalies and judge how to treat the data. So that's all of my talk, and thank you very much for your attention. To get the points, please try the exercise with the related Python tool demonstrated by Bharath in the next tutorial. Thank you.
Thank you, Yuko. I'd like to open up this talk to questions. She provided a very clear and good talk. Thank you so much, Yuko. Does anybody have any questions for Yuko before we move on to the talk by Bharath? If you feel more comfortable, you can also add questions to the chat, and I can help direct them to the speaker. If we don't have any questions, I'd like to ask Yuko to stop sharing and for Bharath to begin sharing his presentation. Also, Bharath put a link in the chat to the drive where you can find the data that will be used in his presentation. After his presentation that he's going to show now, he's going to have a kind of a guided demonstration of his code where participants can take the data set that's provided and follow along, right? So you'll not only get some a presentation from Bharath of how to use his code, but you can actually use your own data, right, or the data provided to follow along with him and ask questions. So this is a very unique opportunity to work with the person who developed this wonderful code. Thank you to Bharath for sharing his knowledge and for making this resource accessible to the community. Also, if anyone is looking, I put in the chat where you can access the e-learning course, where you can download Bharath's source data and some additional resources. Okay, here we go. Are you ready, Bharath? You're muted.
Yeah, sorry. Thank you, Tara, for introducing me. And good evening and good afternoon or good morning to all the participants who are here for this course. And this is a presentation about the application which is developed in the at the BIPM-CBKT project as a part of capacity building and knowledge project of the BIPM time department. So as it is already advertised that this is going to be about the clock data checking and all, clock data checking. So it is developed and validated by Yuko, Julio, me, myself, and Tara and Patricia. So the CBKT project is sponsored by BIPM and IEEE UFFC. And this is also driven by the working group chairs of TAI and the algorithms, Elizabeth and Marina and Patricia, Director BIPM. And this is under the software developer is under the copyright disclaimer of GNU General Public License. Yeah, so this is an overview of application. So once I would like to just give an overview of application and what are the functionalities we try to incorporate in that. Then we can move on to the hands-on session of this application. So So this is how the overview of the interface of the software looks like. So here we have the input configuration where we need to set the input configuration of the uh, uh, files. Like if we have multiple files, description of the file and the data format and the measurement interval, and we can proceed to analyze. So in the left column, so it will show us the details of the input settings which we have done. And this is the functionality block where we can do multi functions here, like raw data, data range selection, detrend, offset, and outlier removals, smoothing, and stability. So in the input configuration, so we have options. We just need to click the upload data files. So here it does provide option for uploading the data files. We need to browse, or you can drag and drop the files, multiple files at a time, and we need to click the submit button. So after that, we need to select the input data settings, either it's a phase or frequency data. If it's frequency, we can select it's 5 or 10 or 100 megahertz. And the description of the file, like each file is a different clock or multiple files of the same clock in order to concatenate the data. And this is a data format. Uh, Whether the data is having MJD timestamping or a date or calendar year timestamping, and the measurement intervals measurements are in the column 2 or 4 as per the file uploaded. Um, Currently, the software can accept only MJD right now, so it will be updated to that. It will be updated to the timestamp to accept the timestamp as well. Then next, we need to specify the measurement interval of our data, like is it 1 second in terms of seconds. Then we can proceed for data checking. Yeah. So once we proceed for data checking, so in functionality block, it shows the a raw sample of the first 1,000 readings, just to ensure that the data is in perfect format, and then it is read perfectly. And then for the further processing of the data, so each file is renamed as clock 1, 2, 3, 4 internally, so that it is easy to when we are processing further, each file or clock data is renamed as clock 1, 2, 3, 4, and 6. So once here we can select the candidates or the possible clock data which we want to analyze, or and then we can click proceed to analysis. Analyze the clocks in other formats. So in the data range selection, so we need to select the data. So this will allow the users to select the desired data range and how it can be used. So how it can be used is to analyze only a specific portion of the data. So either it is we can specifically select the specific portion of the data, and it can and we can discard the data recorded before and after the required timestamp duration, and this will provide visualization of the raw data set. So this is the first stage where we will visually see the plot of the raw data which we have uploaded for that specific clock. So in Detrend, so this is the requirement of Detrend in the data, as just now Yuko madam also explained that it is helpful to identify the outliers. So, and also to check for the frequency offsets, either linear detrending or frequency drift. If we can see the quadratic detrending in the data, after the quadratic detrend in the phase data, we can see that behaviors. So these detrend options help us to find the behavior of the clock. So once we see this kind of behavior in the phase data, so like it is linearly increasing. So that means it has a frequency offset in the clock has a frequency offset um, that can be characterized by the equation x naught plus y naught into t, and the stochastic noise. And then if the clock behaves in this fashion, so we know that it has a negative frequency drift. So apart from offset, it also has a drift. So by applying the linear quadratic fit to the time deviations, that gives us the frequency drift. This detrending helps us in identifying the type of the behavior the clock has, either frequency offset or the drifts, and identify the frequency drifts. And the understanding. So when you can use this tool and analyze and see if you can remove the linear retrend, or if you can remove the quadratic retrend, and you can see the performance. So removing the deterministic quadratic drift enables better visualization of other noises. So on a long term, we can see the other noises in the when we remove the quadratic detrends actually quadratic detrending. So we will get to know when that means we have removed the drift basically. So the long term averaging is being improved. So in the next option we have is offset. So we can remove the offset in the data. So removing an offset, constant frequency or a phase offset does not affect the stability of the clock actually. So either MDAV or ADAV. So once we remove the offset, the new data is bound to be have a mean value of 0. So here we can see that after removal of offset or before that, so it doesn't have any effect on the stability of the clock in terms of Allen deviations, right? And the next option we have here is the outlier. So we can remove the outlier manually or based on multiples of a standard deviation of the data. So here we must be very careful to distinguish a true outlier from a data anomaly in the data. So is it a true data measurement with an anomaly, or it is an outlier in the data? And we can removal of large sections of data. So like this, so if we have some outliers and if we remove that part of portion of the data, so it will cause an artificial increase in the short-term instability of the clock in terms of Allen deviation and MDAV plots. This is because the code automatically concatenates the data set. So here we can see, so when we remove this portion of the data, so here we can see there is a very sharp increase in the short term, I mean, the degradation in the short term performance of the clock actually. So this is what happens when we have any gaps in the data. So Allen deviation gives us this kind of performance as it assumes the data is in continuous form without any gaps. So this is how it behaves. So one must be careful in removing an outliers, one or two outliers, or removing a data set itself, or if we have a measurements which are has a dead time or a gaps in the data. So this we must be very careful to get a conclusion using the Allen deviation tools. And the next option we have in the application is the smoothing. So it can apply moving average by defining a window size. So we can apply a, smoothing using an overlapping window or a non-overlapping window. With a we can define the window size as well for the smoothing, and this helps to uncover the underlying behavior after smoothing. Removal of a fast noise. So this will remove short-term data from the LND, ADEV or MDEV, etc. So when we smooth out the data, so basically we are removing all the fast fluctuations in the data. So that will definitely affect the LN deviation measurements, because it assumes that it basically depends on the consecutive difference between the measurements. Once we smooth them or we average them, so the short-term stability is being affected very severely when we smooth out the data. So here we can see with the 15 seconds of averaging, so we can see this how the performance of the short-term stability is affected. And the stability, so we have here in the application we have options for the to analyze Allen deviation and modified Allen deviation, overlapping Allen deviation, and time deviation. So this is coded in Python. So the it is this portion of the code is being taken from the open source Allen tool available, which to code the analysis in the Python. So as we know, Allen deviation is the square root of two sample variance, and MDEV is used to discriminate between white and flicker phase noise. So I have just mentioned a table here. So just for an context of the discussion itself. So to discuss this in depth, so that itself will be a different topic actually. So just to give to be in the context. So just would like to go through them. Just a fraction, just a overview. So once we see the overview of Allen deviation, so it computes the first difference of the fractional frequency over non-overlapping intervals, whereas modified deviation it averages out the filter. It applies averaging filter, so it computes differences of time averaged filters basically. So this is overlapping Allen deviation. So here we apply the same computing the first difference, but overlapping intervals of to increase the number of samples basically. And then uh, TDEV derived from the MDEV. This is derived from the MDEV itself, expressed in time units basically. This indicates the stability in the time domain. And the main usage is of this Allen deviation is to evaluate the clock frequency stability. And the modified Allen deviation is used to distinguish overlapping noise processes and improves the and overlapping Allen deviation improves the confidence in the Allen deviation estimates, especially in the long averaging times with the limited data set. And TDEV helps us in evaluating the timing jitter. So we can specify that jitter in terms of time, in units of time. So TDEV is basically used in telecom or power grid industries to analyze, to report the measurements in terms of time domain like MTI and TI, TDEV. The sensitivity to noise is like slope. This slopes in the Allen deviation helps us to identify the dominant noise types, but white and flicker phase noise cannot be distinguished from each other using this method. So normally it is be white. Modified Allen deviation is used to distinguish between the white noise and the phase noise. So depending on the averaging filter and the base sampling interval, we can identify the white and phase noises. Here, when we see overlapping Allen deviation, this will increase the statistical uncertainty as it overlaps the data. So it helps us in more overlapping, so more confidence interval. We can have more confidence on the data set. Mm. Just like TDEV, when we see same as MDEV, but expressed in the time units instead of the fractional frequency offset. So in the next option we have is an outcome. So here we can see what are the actions we performed on each clock or on each data set, where we considered clock 1 as clock 5, the name of the file basically, and it indicates what is the type of the data range. So this last option shows us the hmm, what are the all the actions. It will summarize all the actions which we performed in the functionalities tab. Yeah. So I think now we can try this application. So I request the participants actually try to install the application in your local PC better to. Because currently it is hosted on a Streamlit application, so we may have issues. All of us act using it at a time, so we are not sure of that free cloud services. So BIPM is going to set it up at a BIPM host. It is going to host the all the applications in the cloud at the BIPM itself, right? So. Uh, Let me try to open the installed what you say software in my PC. So I would like to run from my PC. Users, if they have any difficulty, please let us know. Or if they are not familiar with so much installation process, so they may use this link to get to the application. So clock data analysis dot streamlit dot app.
Bharath, I just put a link to that in the chat, so people could just go
Yeah.
into the chat. If you look at the last chat message, you
Yes.
can just click on the link directly.
Yes. Yes. Yeah, so just let me open the software in my PC so that
Also, if anybody has questions about Bharath's presentation that he just gave, feel free to put
Yes,
your questions in the chat and I will help direct them towards him, or I can try to answer
sure,
some of them myself.
sure. Thank you. So let me open that. I am trying to open the code in the Visual Studio.
So I'd just like to remind the participants that this is going to be the opportunity that you have to follow along with Bharat and using his code. So feel free to save the sample data that's there's a link in the chat to Google Doc where you can download the data to your PC and you can follow along with his demonstration on the Streamlit app. I put a link in the chat. Um, this is an interactive portion of the technical exchange. So if you're having problems, you can also, um, you can also add questions to the chat so we can direct them to Bharat while he's demonstrating his software.
Sure. So I hope we are here. I think participants and someone confirm or if there is any issue in installing any packages. We also shared the PDF document for how to uh, right. So if this we are suggesting to use the VS Code, VS Studio Code, or you can if you have other versions of Python or another other IDEs also it can work. Right. So you must have a Visual Studio Code or and a Python installed in that. Right. So once you have installed the Visual Studio Code, then you can open it from your Windows taskbar and then type VS Code. So it will open up. So once the Visual Studio is open up, so you can open the folder and you can go to the specific folder where the clock data check application is uh, there. So then you will able to see this part of the screen. So this screen. Uh, and now it will show you all the packages. If they are not installed, it will show you the underlined the packages with underline actually. So if there is any difficulty in installing the packages, so you can install it here. So you can start with installing pip actually. So let me put this in. Then you can install all the required packages in it with these two commands. So you can install -m pip install. So once pip is there, then you can install all the required packages for to run this application. So I just kept these two commands in the chat box.
Bharat, is it
Yes,
okay for me to share your email in case people have questions?
please, please. Yeah. So email, my email address is already mentioned in the slides, so which we will be also sharing here. Yeah. please. You can see my full screen, right?
Yes.
Yes, yeah. So I think if it is okay, can we move forward?
Yes, I
So
have. Can I ask you? There's
yes, please.
a question from the chat
Oh,
about
so
data analysis.
could you share this present in order to follow the steps?
Yeah.
Okay.
So that's one for everybody here, the
Okay.
presentations both from Bharath and from Yuko, as well as the video of this technical exchange, will be available on the BIPM site probably sometime next week. So if you're registered for the course, you'll be able to have access to both the presentations. Even if you're not registered for the course, you'll have access to the video. But I have a question about outliers.
Yes, yeah.
So is there
So
an alarm or a value on the percentage of data that can be considered as an outlier?
can't see the question.
Oh,
Okay. Okay.
do you see it's much further up by FC.
Okay.
And
So
also there's another question that's related to this, asking if anyone knows about an algorithm that's used to detect whether there are large gaps in the data. So I'm not, Frank, would you like to ask your question?
question.
Yes, sorry. Do you have, I don't know if when you remove the outlier, do you have a alarm or a percentage of value are removed? Because it's
Yes.
yeah.
So in the I'm sorry, I tried to answer this question. Okay. So in this application, it also measures once we specify the measurement interval, right? So the application also try to match the intervals between the timestamps actually. So when we say our measurement interval in the data is like 1 second, so it will try to find the difference between the timestamps and MJDs which are in the data. So if there are any gaps, so we can see in the application, so we can see there are gaps, the peaks which we can see in that data. So as we see the demonstration further, then I can show you that how we are able to like how we can see the gaps in the data.
Okay.
Right. Okay. Yeah. Okay. Typical procedure. Okay, there is a question from why is a typical procedure in case of some parent of data was lost due to outlier removal, filling artificial data or otherwise Allen cannot be computed. Right. Yeah. So if we remove the outliers, I think the question is about like when you remove the outliers and fill that with an artificial data, filling that artificial data. Is this how we would like to, and then continue using the Allen deviation? Is that the question? Think. Okay, maybe, mm, right. So maybe I remove outliers and then the question more.
Do you want me to read the question out loud? Or do
Yes,
you want,
actually,
oh yeah, so there's a question that says, I remove outliers using median
median
absolute deviation,
deviation.
MAD, to
Okay, CTS
CGGTT as
processing data
processing data. Could it
in
be
clock data.
used in clock data?
So I'm not sure about that. Applying the median filtering for this clock data analysis, because the CGTTS files readings are every 16 minutes. There is one point, and then we have in the clock data we have every second or as per the measurement interval. Mm, but I'm not sure about that. Maybe someone can answer if uh, they are sure about that. Maybe. Okay. So, so now once the packages are installed, so we can run the program using the command given here, the first line here. So this is the command to run this application, Streamlit run. Then, so it will open up in your local browser in your PC. So it will open up in your local browser in your PC. So once we see the clock data sets, so the clock data sets which are shared has an MJD timestamps and with readings on phase data in the second column. So these are the time interval between them is 1 day, so 86,400 seconds. So this is a sample data of different atomic clocks, real data of some clocks. So we'll try to see the application, try to use this data and see how does the application works. So in the first step, we need to upload data files. So you can open this in the browser as well. So first step is to browse and upload our files. So here is our sample data. So either we can upload all of them together or a few of them as required. So once we submit, then the file successfully uploaded. So then we can see the input data settings. So we need to specify is it a phase data or a frequency, fractional frequency data. Then file description, each file is a different clock, or they are all belong to the same clock, multiple files of same clock. Then we have the data format. So we need to specify the data format either is MJD, or currently we don't have option to read the timestamps because there are there are multiple uh, timestamps formats actually. So the software becomes bulky. So currently we restricted it to MJD. So in the next version, we will add much better features. Uh, then we select MJD. So we need to specify the data column where the data is, and then we need to specify the measurement interval in terms of seconds. So as I said, it is 1 day, 86,400 seconds. Then we can go proceed to analyze data. So we can see here in the left tab, in the left block, so it shows us the what are the files uploaded, what are the our input data settings. Right. So here in the first instance, we can see that it shows us the sample analysis of the clock. Uh, Sample clock initial 1,000 data points, which helps us to confirm that okay, we have perfectly the data is read by the software. So once we select the choice of the clocks which we want to analyze, so we can process the selected clocks. Then we can see the data range selection here from here. So we can see the clock 2. We have a starting point of 56901 and the horizontal axis end data point. So this plot is basically from the plotly plot, where you can save this plot. The three subplots in this plot are belongs to the same image actually. So we can maximize this, or we can zoom, or zoom in or zoom out. So we can select the data range basically. So if we want to, as we can see, there is a phase jump in this data. There is a phase jump of 1000 microseconds in the 1000 seconds in this data. So if we don't want to do that, so we can consider our data point up to here itself. So so that we can mention this horizontal MJD ending to be 58260. So this is our the data set now for this first clock. So this is how we can select the range of the range of the clock. Or if you want to reset, you can come back and reset to the full data. Right. So we can continue with this filter data range 58260. Then this is how we can see the other clocks data. So here there is an option in every functionality to see the combined day plot of all the clocks actually. So here it shows all the clocks. So we can select a double click on one clock to see only that clock performance, or a single click will remove that. If I do a single click, it will exclude only that clock. If we see the double, if we have double click, so we can see only that clock. So at every stage in this application, we have option to download this data. So once we have a new range selected for the different clocks, if someone wants to download, so we can download this data by clicking the option. So here is what the data start range and end range and everything. All the information is here in the text format, CSV format. Right. So the next option we have seen is the Detrend. So in the Detrend, so for each clock we have options of nothing. None means that there is no action or to be functionality to be performed on the data, and we have options for linear and quadratic drift removals in the data. So if we see the linear residuals, so when we select the linear, so this is basically the linear residuals after removing the linear trend in the data, or we can choose the quadratic residuals so that we can remove the quadratic trend in the data. In the same way, we can perform the same with all required data. So right. So we can see the combined clocks. So one of them has nothing actually. So we didn't do any detrend on that. So it remains there. But the first three clocks we did some detrending, linear and quadratic on so this fourth clock 7 is as it is the raw data. So in the offset tab, so already we have removed the outliers. So there is no offset basically to remove the uh, already we are seeing at the residuals of the after the quadratic or the linear trends which we removed for the first three clocks basically. So in this clock, so we can remove this offset if we choose that. So it will give us this just below the every functionality. So here it shows what is the previous and what is the after action. So previous was before removal, the mean value of the offset is 4.73 microseconds. So now it is in minus 22. Right. So we can see the combined clocks plot again after removing the offset. And now we are here with the outliers. So for each clock, there is an option. There are two methods provided here. One is based on the standard deviation. And the other option is manually select the outliers, and you can remove the outliers. Right. So we can select the standard deviation based depending on the data which we have uploaded. So the default option is 5 sigma. So we can change this up to 100 sigma or so. Uh, so let me change this limit to just 1.5. So See, the data which is more than 1.5 times of the sigma is being excluded from the raw data. So here we have this subplot shows us the timing interval or the gaps in the data. So as we have specified the measurement interval to be 86 400. So every day so if some of the days data are missing, so we can see there is a jump in this sampling interval plot basically. So as it is being as we can see that the stability analysis will get very much affected if we have such data gaps in this in the data. So either we can reset to the reset this value, or we can give a different value. So there is no effect of 2.5, and we have an option to remove the outliers manually. So let's perform this in the another clock. So here we have option manually select the outliers and remove it. So here there is an option in the when you click manual selection. So we get two options here. So box selection or lasso selection. So either you can select a box and then you can remove a particular select a particular portion of the data. So and that data will be removed from the further processing. Right. So this is how you can do that. So let me show you with lasso selection is something like you can draw the pattern and you can remove that specific outliers. Or if it seems to be if you want to remove a selected portion as well, so you can normally zoom. So zoom to particular portion and then you can select that particular portion, or you can even zoom and remove that two data points. So in this large data, when we remove 2 3 data points also, we can see there is a gap in the data. So this subplot shows us that the data has some gap here, right? So this is how we can use the standard deviation based and manual selection outliers. Basically these are the currently two options are provided uh, same way. So we can do that for all the clocks as well. So this is the combined plot. Once we can see here, we can have a conclusion of what we have done. So for clock 2, we did the standard deviation based filtering. Clock 4, manual selecting, and clock 6 and 7, we didn't do anything. So after removing the outliers, you can download the CSV file and you can re-upload the same file to the same application if you want to do some other analysis. And then here we have option for smoothing. So we have options for moving average non-overlapping filter to apply, and the moving average overlapping filter we can apply on the data. So we can select the window sampling window for that. So here we can see we can zoom and see. So we have selected 50 data points. So it takes us 1 to 50 data points and averages it out, and it is non-overlapping filter basically. So once also have then a moving average and overlapping filter, we can set the required sampling window, apply for that. So this can be done for different clocks data. And again, we can see the combined plot, and here we can see our action. So we applied moving average overlapping filter for this data, and the sampling window is 10. So the mean value is this, and the standard deviation is this after the applying the sampling smoothing. So here again, we can download after smoothing the data. We can download the processed data basically. Then here we have option to see stability analysis. So this part of the code is taken from the Allen's tool, which is an open source code in Python. So here we have options for the Allen deviation and modified Allen deviation, overlapping, and time deviation. So here we can plot all the clocks together to see their performance. right? So here we can see all the clocks together, and you can download this plot, and you can download the LN deviation data as well. So here is the data. So that is the range we selected for that clock, and for that particular range, these are the results for a tau measurement interval and the clock 2, 3, 4, 6. Right. So similarly, we have options for MDEV and overlapping LN deviation. So just below the ADEV, we get the MDEV, modified LN deviation, and this is overlapping LN deviation. Then we have time deviation. So the applications which are deployed or developed in the Streamlit as a inbuilt has a basic feature that the entire application reruns when you perform some action on the application. So that's how it reruns the entire application. So it is a overlapping LN deviation, and this is a time deviation. So for each set of action, so we can download the plots or we can download the data as well at each stage. Then we have the outcome. So here in this tab, we have the outcome of the data. So like LN deviation analysis, the ADEV values for all this, all the clocks. So whatever actions we have, MDEV analysis values, and TDEV, OADEV, and values. So we can download all this information as a text file if we want to do any further processing of that. So this is the overview of the actions which we performed. So in detrending, we applied a, quadratic detrend. So that's the equation, best fit quadratic best fit equation, which is for that specific data. Right. So this is the overview of using the application actually. So if anyone has any queries, please we can discuss for some time before we do a few test cases. Ah, is there? Yeah, there is a question in the chat like from Bing Wang. It seems that a frequency jump happens for the clock too. Can we process the frequency jumps of the clock with the tool? Yes, I will show you in the next test case. So how we can segregate that. We can use the data range and we can do the analysis separately. Right. Big one. What do you mean by process when you can set the range or which the process that is? Yes, I
Sorry,
think
but
Julio
so
has.
Bharat, I was answering the question in the chat,
Sorry.
but I'm having a
Yeah.
bit of a challenge. I'm following along with your Streamlit app, and so I hit upload data and I browse
Yeah.
files, right?
Yes.
And I add some clock data, right? So
Yes.
it says upload, okay, and then in the raw data, I remember. See, I have to be able to see the data, right? I have to first I have to put in the input configuration, right?
Yes. So input
Okay.
configuration. Yeah. So from this input, once we are done, so we need to click the proceed to analyze data option. Once we are clear with the measurement interval settings and the data format, so we need to set this actually. So because every user has their own requirements and the data format. So okay.
So there's like another question
Yes.
in the chat. With a big
Yes.
gap on the data, how can you calculate the ADEV? I think in the Allen tools library, the values are concatenated, so the ADEV will be wrong. Is it possible to replace the move data by calculated data?
Yes, it is correct. So Allen deviation. So we have mentioned the same here. So Allen deviation, so gaps in the record of the clock data can result in incorrect estimates. So we have already had a disclaimer about that. So currently we in this application there is no feasibility that we have added to uh, add calculated data in the gaps and to perform the Allen deviations actually. So yeah, so that was the actually we may take up in the next versions of this tool actually. Right now.
So to the participants, are you guys able to access the Streamlit app online? And
Yeah.
are you able to upload your clock data and look at the raw data? Because if you can't get back past that point, it's going to be difficult to follow along with Bharath. If you have any questions about that or challenges, it would be a very good time to ask for help now. Because we want to make sure that as many people as possible can follow along because these are very useful tools. So works fine. And as I see that people are saying it's working fine, are you able to view the data and raw data and select the clocks that you'd like to analyze as well? Yes. Okay, that's good. If anybody's having any troubles, feel free to raise your, well, it's very hard to see people's raised hands, but if you could put your question in the chat, it says, so somebody is using the online app, but my data is not showing. So one thing I've noticed is that you have to be very careful. Once you've uploaded the data, you have to go to the input configurations to input data settings, file description, data format, measurement interval, right? And you have to fill these in before uh, you can actually see your data. Marcelo, can you try that and then let us know um, if it works better after that? Thank you. Okay.
So once we upload the data, so we need to press this button, proceed to clock data checking, proceed to analyze data. So right, so we need to click this button so that the data gets a readout, read by the software. Yeah. So okay. So I have a few test cases quickly. So users can test them, use that data, or you can upload some other cases as well. So here, so how does the effect of detrend on the data? So as we can see, like once we remove the data or we remove the detrend the data. So let me just refresh the application. So I will upload the record the sample a sample file. So what I shall do is, so now I have clock 3 data. So I will just copy and paste it here with a different name. That's it. The same data of the file with a different name. So now I will consider these two as my input files, and then let me submit this. So once I submitted, so I need to set the settings. It's a phase data, and each file is a different clock. I consider them as different clock, and the timestamps are in MJD, and the data is in the second column, right? And the measurement interval is 1 day, which is 86400, and then proceed to analyze data. So and now I can select these two clocks, right? And without, and then process selected clocks. Now I can see in the data range, the data is read and the full data range of both the data are same basically. So once we want to see a specific behavior of the stability, once we detrend the clock or once we without detraining. So the clock 1 and clock 2 are currently, I have uploaded the same data files. So it is of same data basically, right? Clock 1 and clock 2. So in clock 1, let me put the raw data, and in clock 2, let me take the quadratic residuals, right? So now we can see the stability of that, right? Let's see. So we can see the clock 1 is a raw data which we have selected, and the clock 2 is less we detrended the quadratic behavior in the data. So we can see that Allen deviation in the Allen deviation, so it doesn't affect any short-term behavior. So it helps us in improving our long averaging interval. So that is what I have showed in the presentation as well. So how does the detrending affects the stability of the clock, right? So in the next test case, we can see effect of gaps or dead time in the data on the stability of the clock. So what we can do is, in the same, for example, in the same file, so let's consider, let's not detrend the clocks, or basically clock 1 and clock 2 are both same data currently. So the intention is we can to see how a specific application, how does the effect of detrend, how, what is the effect of offset, or what is the effect of outliers on that. So one of the clock we remove or we perform that functionality, and let's shift to the stability. So now the clock 1 and the clock 2 are same data, so let's go to the outlier part and let's delete some data. So let's keep the clock 1 as a raw data, and clock 2, let's delete some, manually select some portion of data and delete that. Right. Now just click on the stability. So we can see the clock 1 is a normal behavior of the clock with continuous data, and the clock 2 is the data where we have removed intentionally some data. We have created a data gap in the data. So here we can see, so if there are gaps in the data, so when we try to analyze the stability using the Allen deviation, so this is how it behaves. As Allen deviation measures assumes that the data is continuous, so that it does just keep continue measuring the difference between the consecutive measurements and just try to perform the analysis. But if there are gaps in the data, so we can see that Allen deviation gives us a different result. So one must be careful with the gaps or removing a bulk outliers actually. Right. So you can also analyze using just if you remove one, two data points, what will happen, or you can remove the starting or ending points. How does it happen? So with this interface, it's very simple to understand the analysis of the stability of the clock with the various functionalities, basically. Right. So this is what in the outlier removal also you can test it yourself, and effect of offset removal. So as we can see that offset, when once we remove the offset, it doesn't affect any stability actually. But we can see the interesting part as phase jumps. So someone was asking about the phase jumps. So let's try to see how we can analyze the phase jumps. So instead of uploading a new file, so let me refresh the application and browse. So as we said that phase jumps, we need to see the clock UTC clock 2. So what we wanted to do is we just rename the same file, just copy and paste it, right? Clock 2, clock 2, clock 2, and clock 2, for example. So I am just taking the same data with different file names, basically. So let me submit that. These input configurations are already set to this particular data format, right? Right. Now proceed to analyze. Now let's select the 4 clocks, right? Right. Right. See, here we have a data jump, big data jump in the data, phase jump in the data actually. So what we can do is we can analyze this portion separately, and this portion separately, and this portion separately as well. Right. So in this way, we can find the stabilities in different set of data as well. So for clock 1, let's keep the full data range, and for clock 2, we can select the starting endpoint 58260. Right. So this is the first portion. Now, as clock 3, we can select this portion of data. So the starting point of this is 58261. Okay, and the ending is 58456. Right. So this is the middle portion, and this is the end portion basically. So 58457. Right. Okay. So here we can see the combination of all the clocks together. Clock one is the exact full range of data. Clock two, three, four are three different parts of the same file basically. So in case of detrending, so we can see clock one is a raw data basically, clock two, clock three, and clock four. So if we want to see how what is the performance in terms of stability, we can directly go to the stability and we can see the options. So this is a clock one. The performance is very bad in the range of tempo -4 and so. So in clock two, that is a first portion of the data where we have selected. So it is performing much better. So, and this is a clock three, where it is a middle portion. So data is very short. So we have just one point, and we have clock four, which is the end portion of the data. Again, it is also fine. So, but this yellow legend plot, that's how performance looks when the Allen deviation, if we use Allen deviation with the jumps in the data, phase jumps in the data, or the constant frequency offset jumps in the data, right? And we have periodic phase corrections and frequency steered phase data. So just wanted to show you that as well. So once we have a constant frequency phase corrected data, so this is a phase steer data set basically. So this data is in the link which just I texted in the chat box actually. So phase steer data. So here let me show the data format. Phase steer data. So here in the first column is the MJD and the second column is the data, right? So upload files uploaded, input settings, phase data file each only one. It's MJD and second data format. Measurement interval is 1 second. Okay, sorry. Then we can proceed to analyze this data. Let me select this clock and this. So here we have the behavior of the clock. So we can see this kind of behavior. So at every, sorry. So we can see the drift is compensated in terms of phase at every periodic range actually. So we can see this kind of behavior in NTP steering as well. So when there is a clock is intentionally corrected when between the predefined set of limits, right? So now we can see perform some analysis on the stability using this clock. So since we can see that every in short term, so it is being corrected, the phase jumps. It's a periodic steering of the clock. So we can see that the stability is very bad in the short term. So as the long term, it try to improve it actually. Yeah. So these are the few test cases which we can see, and the other test case was analyze different portions of data. So just now we have seen the how we can segregate, upload the same files with the different names, and we can select different ranges in the same data, and we can analyze the stability, combined stability, or the portions of the data, or you can apply different detrend in that portions of the data, and you can analyze the stabilities of that, or if you want to remove some outliers also. If you want to do some backward tasks, like first you want to remove the outlier and then come back to do the range selection. So you can do that. Like if you directly go to the outliers, first remove the outlier, then download the data. So every functionality is provided with an option to download the data in CSV format. So you can upload the same file in the application so that it can read and then continue. You can continue processing the functional application which you want to do, right? So if so you can if you start using that application, so you will get to analyze various situations basically, right? So this all information on how to use this and a demo tutorial of this application and the software code link for that is all there in the clock data analysis with a better version of that as well. So I request people participants to register for this course and please let us know for any queries to the email which is mentioned in the description of the course in the BIPM e-learning platform, right? So maybe if we have some questions, we can take it for the regarding the application installation or operation of that usage of the application basically.
So I'd like to thank Bharath
Yes.
for his very wonderful presentation, his demonstration of his
Mhm.
software, and also for developing his software. I had not mentioned it before, but Bharath actually served, and Yuko both served as CBKT capacity building coordinators at the BIPM. I'm waiting to
Yeah.
see if there are any questions in the chat. There was a question and I answered it already, Bharath.
Yeah.
So
Yes. Yes.
was
Thank you.
anybody having any challenges with accessing the code or uploading any data? Does anybody have questions for Bharath or Yuko on this presentation?
Mhm.
There's one message. Okay. So from the chat, Bharath, I saw that a lot of people had no problem accessing the Streamlit app, so that's good. And
Oh,
somebody
nice.
just mentioned that your code worked very well, so that's nice.
Oh,
Congratulations
nice.
to you.
Yeah, we need to improve in the next version with all your collaboration, and then we can see the better results. Yeah.
I also included Bharath's email in the chat. The chat's gotten quite long, but his email is there if you have questions on his code.
Yes.
So are there ways to remove or compensate phase jumps in the calculation of UTC in BIPM that are not implemented yet?
There are ways to
Although
remove
they are not
components.
implemented yet?
So
This might be a
that means
question to
question.
Patrizia.
Yeah. Ways to remove or compensate phase jumps in. Don't implement. Yeah, I think maybe Patrizia madam can answer that.
Yeah, I'm sorry, I'm trying to
Yes.
understand the question. I'm not sure I understand.
Yeah.
So, Wong Sun, you are saying that you would like to remove or compensate jumps before submitting the data, or are you asking if we do that in UTC?
Okay, can you hear me?
Yes.
Yes. So we basically, when we submitting our data, we remove all the phase jump, and if there's, but I just wonder if there are any special way to remove or compensate phase jump when you are calculating UTC or EAL. Even though every institute are trying to remove all the phase jump, there may be some possibility that there is still some phase jump in the clock data. So in that case, how do you remove or compensate to get the right phase data to calculate EAL or TAI? That was
Yes, yes. As you say, we need the data without jump in the computation of UTC, not to degrade the stability of UTC. So when you submit the data, you also submit the information on jump that have been voluntarily applied and that are known. In that case, you submit the epoch of the jump and the amount of the jump, and we compensate it, because if we know that there is a jump like that, we correct the past by the amount of the jump that you have declared to have the data continuous. We do that only when the jump is known. So when you tell us at what epoch and which is the amount of the jump. If we observe jump and we ask you, but there is no clear understanding of what happens, in that case, maybe is an instability of the clock. And so we deweight the clock. We put the weight of the clock to 0 to avoid that this unknown jump affects the stability of UTC.
Okay, thank you.
So I think there is a question in the chat. Could this app be used to calculate an ensemble of clocks? So currently the application is only to analyze the clocks in a individual with considering them as individual clocks. So there is no options to that so that we can make an ensemble out of the clocks actually. So that is not part of the current application actually. So it is only for analyzing the data individually. Right? Yeah. Yes.
So I'd also like to add that the BIPM is also creating a course related to timescale averaging that will be released later on, maybe in a few months. But we will be having another technical exchange on that topic in particular, June 25th.
Okay. So
to the audience, are there any more questions?
So just as a test case, I have uploaded the GNSS data as well here. So you can do some kind of processing using your GNSS data as well, not only the clock data. So maybe users can upload or may try to use the application, and if they can give us some feedback, we can have this application to take it to the next version and for a better experience and all that. So they can calculate the stabilities or they can do smoothing on the data or applications. So not only the clock data, so we can even upload the GNSS or some other data with the proper format without any gaps, or we must be ensuring that how much we can do. Right. So I think we are on time.
Bart, can I ask a question?
Yes, yes, please.
If I'm looking at this data, right, the blue data, at the beginning of the data set, you have these two little outliers here. How do you know if those are, right, if that's an outlier, if that's actually real data?
So I am not so much familiar with that, but basically when we analyze that in different situations, depending on the measurements, it will be defined to be like 1.5 sigma or 5 sigma, or so the basic filtering which is applied. So we considering the experimental scenario and considering other parameters of that. So in case of GNSS, there are situations of like a loss of lock where the receiver loses the loss of lock, or due to some perturbations in the ionosphere. So we have some basic intuition of the data, or how it can, what could be the cause of that point or that data. So it depends on, in particular cases of clock, how does that kind of behavior happen. So I think we should have some particular some background intuition to understand that actually. So we cannot put a benchmark on that. We need to have that anything more than 2 sigma or 5 sigma is an outlier basically. So we must correlate with the experimental setup or behavior and the parameters which basically contribute to the measurements. Yeah. Yeah. Right.
Thank you.
So yeah, thank you. Yes. So right. So I think, are there any questions? Okay. Mhm.
There aren't any more questions in the chat.
Okay.
Does anybody have any last questions? Otherwise, we'll close the technical exchange pretty shortly. But before we close, I'd like to share one last slide, Bharath.
Sorry, I just let me stop sharing.
Okay, where do I share? Here we
Okay.
go.
Right. I would like to thank BIPM for giving me the opportunity to present this application as the technical exchange.